Good morning, everyone, and welcome to the WREN Webinar, Experiences from Conducting Environmental Research at Land-Based and Offshore Wind Facilities. This is Sam Ramsey filling in for Paige Johnson from AWWI, who's on vacation today. Before we get started, I have a couple quick notes on logistics. For sound, you should be able to hear us through your computer or over the phone if you dialed in. If you are on the phone, please make sure to mute your line. If you are having any technical trouble with the webinar, please send us an email at cmarshall@awwi.org. You can find Christina's email in the notes pod. You can also send us logistic questions through the Q&A box in the webinar room. We'll be doing a Q&A session after each presentation. If you have a question, please enter it into the Q&A box at the bottom right of your webinar screen. You will only be able to see questions you submitted in the box, not those submitted by others. So feel free to type in questions whenever they come up, and after each presentation, we will read the questions out loud for presenters to respond as time permits. And finally, a reminder that we will be recording this webinar to post on the WREN website along with the presentation slides. And so now I'll turn it over to Chris Hine, Senior Project Leader for the Environmental Portfolio at the National Renewable Energy Laboratory, to introduce the speakers and give a little background about WREN. Chris?
Thank you, Sam, and thanks for the introduction for today's webinar. Just a quick background on WREN. WREN is one of the tasks for the International Energy Agency's Wind Technology Collaborative Program. WREN is assigned Task 34 and stands for Working Together to Resolve Environmental Effects of Renewable Energy. And one of the tasks, or one of the activities, I should say, that WREN performs is to disseminate information on wind and wildlife issues, and we do this through a number of avenues, one of which are these webinars, which are intended to support international collaboration and understanding of wind and wildlife research. These webinars are recorded and can, if you go to the TESIS website, which is shown here on the slide, and go to the WREN page, you can view any of the previous webinars that we've held, as well as other documents that have been produced by WREN. Just a quick status of where we are with WREN. WREN began in 2008 and finished its first 4-year phase in 2012, and then was extended for another 4 years. And so right now we're starting, we're in the process of proposing a third phase for WREN that'll extend for another 4 years through the end of September in 2024. This new phase that we anticipate going into will continue some of the work that we've done in the past, such as managing and enhancing the TESIS website, which is performed by the Pacific Northwest National Lab, as well as disseminating state-of-the-science information. A couple of new activities that we're going to do in the next 4 years is, one, evaluate the global wind energy and wildlife priorities. And this will be done through a systematic horizon scan, where we'll engage with the international community on the top priorities for both offshore and land-based wind. And then the other new activity is to develop a monitoring and mitigation technology database that would be housed on TESIS. So today's webinar is to discuss conducting environmental research at wind energy facilities. And this is not an easy process, as anyone who's done this knows. It requires constant communication among all of the different partners, extensive planning of logistics, and efficient implementation for the project to be successful. And so today we have perspectives from both Europe and research conducted in the offshore environment, and North America, and kind of lessons learned from conducting research at land-based wind energy facilities. We have two speakers. The first will be Dr. Paul Thompson, who is a professor of zoology at University of Aberdeen's Institute of Biological and Environmental Sciences. Paul has used long-term individual-based studies to explore how environmental variation influences the behavior and ecology of marine mammal and seabird populations. Over the last decade, these studies have underpinned work that his group has conducted for regulators and industry at offshore wind farm sites in the Moray Firth in northeast Scotland. And then we'll have Stu Webster, who is with the American Wind Wildlife Institute beginning in 2017. He's a senior program manager for the Technology Innovation and Research program at AWWI. Prior to joining AWWI, Stu was the Director of Permitting and Environmental Affairs for Iberdrola Renewables development, construction, and operation of over 5,000 megawatts of wind and solar facilities. Prior to Iberdrola, Stu was the Senior Permitting Manager for Clipper Wind Power Development from 2006 to 2009. Throughout, Stu served in leadership roles on various wind energy stakeholder committees, a member of AWWI's board, and engaged in all manner of exciting topics in policy development. The axiom that between two opposing viewpoints, there is always common ground. Stu's educational pursuits concluded with a master's from the WREN School of Environmental Science and Management, Santa Barbara, California, and Stu calls Portland, Oregon home. And I also want to thank our two speakers for today, and also thank AWWI and Kearns & West for hosting this webinar. And with that, we will move ahead to Paul's presentation. Paul has provided a pre-recorded presentation for us today, and we'll get that loaded up here. Thank you.
Hello, I'm Paul Thompson from the University of Aberdeen. Thanks to Chris and everyone else there for asking me to present at the webinar tonight. I've been asked to talk about our experiences conducting environmental research around offshore wind farms, and we're based up in the Moray Firth in the north of Scotland, based from a small research station in Cromarty here, which is about 120 miles from the School of Biological Sciences that we're linked to at the University in Aberdeen. And this is an area which has got important wildlife populations. As you look out here to the mouth of the Cromarty Firth, this is a core area within a special area of conservation for bottlenose dolphins. And then as we move round into the Cromarty Firth, on the other side of the firth there, you can see the turbine jackets for Moray East Wind Farm, which are just waiting to go out. This is a bit of video I took a couple of days ago out to the construction site out in the middle of the Moray Firth. We got involved in work on offshore wind farms primarily because we were already conducting population studies of key receptors, marine mammals, in the area long before people started developing offshore wind farms in the UK. In this case then, the opportunity to get involved in this kind of research was a case of new developments in an area where we were already working and where there were important and protected wildlife populations. Our work has primarily been focused on 3 species of marine mammals: harbour seals, bottlenose dolphins and harbour porpoises. I don't want to talk in any great detail about the results of our work or the detail of those studies, but it's useful, I think, to highlight a bit more about some of the approaches we've used and the techniques that we've had to adapt and develop to use at these sites. The map on the right there shows both the SACs, the special areas of conservation, which are of particular interest in relation to these protected species. Our own location down there in Cromarty. And then the location of actually some earlier oil and gas related work that we did during some seismic surveys. But the 3 offshore wind farms that we've been working with over the last 10 years or so now. So Bowl, the Beatrice offshore wind farm, which is now constructed, Moray East on the right there, and Moray West, which is consented but not been built yet. In general, we've been trying to understand the drivers of change in these regional wildlife populations and developing methods where we can assess perceived potential impacts for consent applications, and then carrying out work during construction to test some of those assumptions that have been made and looking at responses of wildlife to different phases of construction and operation. So in that respect, our work has been carried out long before the wind farm went out there, during the consenting application, and then now we're still in the middle of construction of the second of those. One of the key points to bring out from that is that this is a very long process, and I'll perhaps come back to that in a number of ways, but the work started back in 2010 when we were involved in pre-consent surveys to feed into the environmental statement. There was then a pause in active research and survey during the consenting process, and then we moved into a period of pre-construction surveys and construction surveys, and in the future we hope to be involved in carrying out post-construction monitoring work as we see how animals respond to the presence of these jackets. It's also useful to highlight that our research involves two main threads. The first of those has been developing existing population studies, which have primarily been on these protected populations which use coastal waters at quite a distance from the offshore wind farm sites, where we're monitoring potential far-field effects, particularly from construction noise, which might be affecting these species, and those are individually based studies of harbour seals and bottlenose dolphins, where we're slotting in these monitoring studies to at least 15-20 years of baseline data. The second approach involves carrying out studies actually over and around a buffer zone around the offshore wind farm sites, and that zoomed in map there shows the three sites that we're interested in. In the Bowl site on the top and the Moray East one, the pale spots are the turbine locations, and the red dots give you an example of one period when we had more data loggers at these sites, where we're using passive acoustic monitoring, for example, to look at responses of porpoises to construction noise from piling. So in this case we're having to integrate moorings to all the other construction activity. The other approach at these offshore sites has been to conduct aerial surveys. This has particularly been important for seabird surveys, both pre and during and post construction. And then finally there's some work where we're conducting similar transect surveys, but in this case from boats, where we have to negotiate either a constructed or wind farm or a wind farm under construction. In terms of opportunities, there are some great opportunities for strategic research, and we developed a strategic research program with the regulators and various other stakeholders, and that then gives access to partnership funding, which as a university researcher would be difficult to tap into using conventional sources. I think another great opportunity is also that we can co-develop interdisciplinary projects, and particularly identifying projects that have become possible because we've been involved with the wind farm companies and their engineers at a very early stage during design. And that presents opportunities for the integration of environmental data collection into engineering processes and the structures, although I think that's not been fully exploited, and I'll come back to flag that at the end as one thing that we could do more with in the future, I think, in some of these studies. The four main challenges that I want to highlight, and which I'll go into in a bit more detail in each case, are first of all those timescales, that we are dealing with such a long process, but also we're dealing with very different kinds of deadlines and timescales when we're particularly working as university researchers with our other commitments to university calendars and teaching and so on, compared with industry timescales and government policy timescales as well for particular requirements at different stages of the consenting and build process. Then we've also got environmental challenges, and perhaps that's one of the, on top of all the usual environmental challenges of field work, we are working in a windy offshore environment, in this case in the north of Scotland, in pretty temperate conditions, so that's challenging. There are also structural and cultural challenges when we try and carry out work which involves university academics and a range of other stakeholders and industry. And linked in with that, the logistic challenges faced by working offshore with a fairly new and growing supply chain. Looking at each of those in a bit more detail, as I showed in that earlier figure, it takes a long time to plan and build a wind farm, even when everything goes smoothly. The Beatrice offshore wind farm, which was commissioned last year, 2019, we were involved in consent applications back in 2010, so it's taken quite a while. And through that period there's been uncertainty over the timing of different phases. We've worked on these two different projects, Beatrice and Moray East, which are side by side, and originally they were planned to have been built at the same time, which made the predetermined ideas about what might be pre-construction and post-construction monitoring quite straightforward. But in fact, for various commercial reasons, they've now been built sequentially, which brings new challenges to the timing. Having said that, each of those phases, although the timing of them might be uncertain, once they're in flow, they can come with very tight deadlines, and that can create real challenges when it comes to procurement and contracting. Some of this also sort of feeding into that cultural difference between industry and university procurement and contracting. So in many cases, we've been needing to start to do pieces of work almost before, or certainly very, very close to the window when we were getting a contract. And the work that we've done has only really been possible because it's been part of this long-term program where we already had equipment and infrastructure and logistics in place, and indeed staff in place to carry out some of the work. In terms of the environment, that physical environment offshore is an extremely challenging workplace, both for building a wind farm and also for carrying out the research, but particularly where you're trying to do research which is tied into particular phases of the development, where, for example, we were wanting to carry out work exploring how animals were responding to power driving. We may be working from vessels which have got a much narrower weather window than the large offshore piling vessels, so it's quite possible that some of those phases of work would go ahead at a time when, from an engineering point of view, they had a suitable weather window, but from a research and monitoring point of view, we were a bit more limited. And that's why we tended to, wherever possible, use techniques where we could, for example, use long-term moorings, where we could put equipment out before the event happened and then leave it running on the seabed until afterwards. But it's a very complex human environment to negotiate as well. Some of that's related to the project and the other vessels that are going on, and some of it's down to the other stakeholders involved. So sticking with that example of the offshore moorings, for the Beatrice offshore wind farm, they were using a piling vessel which had 8 anchors stretching out almost a kilometre, and vessels taking those anchors in and out amongst the equipment that we had moored on the seabed. So we had to work closely with the project team to work out where they were likely to be putting their anchors, and to try and make sure that we were deploying bits of kit in an area where it was at least risk from that kind of equipment, that kind of activity. But at the same time, you've got other stakeholders on the site, and in these waters, fisheries have been carrying on in and around wind farms. So some of our bottom-mounted equipment is also vulnerable to fisheries damage, and we have lost bits of equipment due to trawling during key parts of the monitoring process. The structural and cultural challenges, we're working within very different health and safety cultures, and they're not necessarily conflicting, but they are different, and often that can mean additional certification and checks, for example, of vessels which might be already certified to carry out this kind of work. Very often a new company coming in will want to do their own certifications, and that's something else that can add to the challenges when you're working on tight timescales in difficult weather windows. It may also mean that you've got multiple licensing and reporting requirements, and we've found that working with the wind farm companies, we've had to have a much higher level of short-term reporting, even down to the day-to-day reporting, saying we're going out in the field today and telling them when we're back, as well as monthly reporting, which may be less familiar to many people working in academic structures. Not in itself a problem, but one needs to make sure that you've got mechanisms in place to easily fit that kind of reporting schedule into your normal processes so it doesn't become too onerous. Another thing that we hadn't anticipated earlier on is we recognise that this is a long process, but each of those stages of the wind farm development and sometimes in between as well, with its consenting, moving into construction and then operation, will often involve a change in company structure. Generally, other companies buying in as the project gets further down the road and more expensive. And so that can also mean that internally with the company that you've been working for a number of years, there can be cultural changes or structural changes and turnover of staff. So it's very important to build relationships in such a way that they don't depend on a few key individuals who may move into other posts, and that you can carry on developing those relationships as company structures change. There are also other changes in key parts of the supply chain which may affect what you're doing as well. And the supply chain is certainly an issue when it comes to logistics. With a lot of these big projects, we were focusing on marine mammal research, but there are other companies, particularly early on during consenting surveys, who would, for example, doing seabird surveys or benthic surveys. And locally in an area like this, where there's not a history of this kind of development, you may then suddenly find that you've got competition within local supply chains for vessel availability, and that can make it especially challenging when you're all trying to work within similar narrow weather windows. And your research needs to be adaptive because, not least of all, of changes in timescales in the project where you've got particular bits of work linked to key phases in the development. You need to be able to cope with the fact that piling has just stopped because the hammer broke and they can't get a new hammer for another month. Although it's a very large research project for a group such as ours, it's a very small part of a £2.5 billion project. So you need to be working around those other aspects of it. So that's where it has been particularly critical to invest in collaborative partnerships. In the case of the survey and monitoring for the wind farms in Scotland, these are overseen by regional advisory groups, which include industry partners and all the main bodies involved in regulating and advising regulators, as well as some non-governmental organisations as well. And that dialogue throughout involves a lot of investment, but is incredibly important to allowing the project to develop effectively and also adapt as there are changes in other aspects of the development that I've highlighted earlier on. Finishing off with a slide here then with lessons learned. One of the things that's been incredibly important is having a long-term strategic framework that we're working within. Although each phase of the project might only be funded for 2 or 3 years, the fact that it's part of a strategy where there's an expectation that that work will carry on, and the key partners have been talking about that for some time, has been incredibly important in maximising the science outputs. And by science outputs I mean both the academic interest of the research that's possible, but of course also being able to carry out work that's really useful for the industry and the industry as it moves forward at other sites as well. And one of the key things that we have tried to do is to use the monitoring programs not just to tick boxes to meet consents, but to fill data gaps that were identified during consenting, reduce uncertainty in parameters that appeared important in some of the assessment models, and so on. And conversely, when one's having to have very short and unpredictable lead times for projects where a huge amount of effort is spent racing around trying to organise logistics and contracting, then that really can constrain the science, and also constrains your ability to maintain critical mass and continuity of researchers, availability of equipment, and indeed relationships with the supply chain, particularly boat owners that you rely on for this kind of work. Nevertheless, I think the other thing that I would add, I mentioned at the beginning about opportunities for integrating some of the monitoring and research that we might be wanting to do into the physical infrastructure of these wind farms. That's something which I'd always hoped we could do more of, but I think that what we've realised there is we have to start talking about this kind of thing much earlier in a development than we realised. It's no good once the wind farm is being built suggesting that we might attach a bit of monitoring equipment to the outside of a turbine jacket rather than leaving it on the seabed where it might be vulnerable to fisheries, because the engineers have already done all their calculations about weight loadings and so on. So I think this is where we could have much more effective co-development as we move forward, trying to anticipate some of the monitoring requirements, particularly those long-term monitoring requirements post-construction, and seeing if we can't integrate those into the design of these projects. And that in itself will do much to reduce the need for boat and aircraft and additional personnel out on the water, which in the end can improve the science, improve the safety of everyone involved. And
if you've got questions, for those of you who were able to hear it, then happy to take those now.
No questions. Maybe we will move on to Stu's presentation. If you do have questions for Paul, you can type them into the Q&A pod, and we can get those to Paul and have him either answer via the Q&A or via email.
Good morning and good afternoon, everyone. My name is Stu Webster. I'm the Senior Program Manager for AWWI's Technology Innovation Program. And I want to thank NREL particularly and the WREN community for inviting me to present today on research and development and testing opportunities and challenges for wind wildlife research, with a particular focus on technology as it relates to the onshore environment. And my presentation today is going to cover the following topics on the lessons learned from each, with a primary focus on technology evaluation studies, which is our primary experience and objective in the Technology Innovation Program. However, it should be noted that many of the lessons that we're talking about today can be applied to non-technology related research, both onshore and offshore environments. Brief introduction to AWWI, whose mission is to facilitate timely and responsible development of wind energy while protecting wildlife and wildlife habitat, is principally undertaken through a broad diversity of collaborators making up the wind industry, conservation, and regulatory stakeholders, and even within the wind industry, a broad diversity of developers, regulated utilities, independent power producers, and turbine manufacturers. And while our primary focus is on the domestic U.S. market, we do have international representation as well as collaboration opportunities. One example of this collaboration is the National Wind Wildlife Research Plan, which underpins all of our research priorities at AWWI. Along with summarizing key species of concern and research prioritization thereof. It also provides some insight to the state of the science and suggests the direction of wind wildlife research, such as testing hypotheses on the variation in wind wildlife risk, promoting the replication of findings while not unnecessarily delaying practical implementation of research findings, through existing mechanisms such as adaptive management, the practical application of research findings, and making a stronger connection with further research questions to be answered, and decreasing the instance of conservation decisions and science that inadequately consider the long-term risks of deferring actions on climate. Key attribute of this plan throughout for all the species of concern is the development of technology solutions of impediments to the timely and responsible deployment of wind energy. Which brings us into the Technology Innovation Program, its focus, which is enabling solutions for the monitoring and reduction of impacts, transforming essentially the way we assess impacts, as well as increasing the options for reducing impacts deemed excessive and unusual. Hallmark feature of the Technology Innovation Program is connecting otherwise disparate parties to achieve efficient and effective execution of technology research, the outcomes of which reliably and objectively inform all wind wildlife stakeholders, with a primary focus on informing the technology market. Pivoting to the objectives of the market, it's obviously principally to expedite the development of technology solutions, informing and potential active and potential participants in this technology solutions market, the buyers, the sellers, innovators, investors, and public and private conservation interests that are all relying on solutions to address the impacts deemed beyond the norm. We're attempting to generate a robust technology market in order to drive down mitigation costs, increase optionality, and reduce uncertainty. In the process, technology is assumed to be improved in a more efficient fashion by making more informed R&D investment decisions to advance technology. The solutions need to be user-friendly and fit within the constraints of the end user. Increasing insight and accessing end user knowledge for the vendors and innovators is one of the key areas of what we deem to be universal success. The replication of studies and informing the R&D process maximizes the value of even interim efforts of smaller research efforts in addition to large multi-year type efforts. The vision of third-party assessments and the publishing of peer-reviewed findings and results provide a low-cost, expedient, and transparent market signal for what works, what needs more work, and where restricted investment opportunities should be focused. And equally important, building a body of knowledge and information on the cost to acquire, implement, and operate these technologies further energizes innovation and informs plans for adoption, ideally leading to cost-effective, proactive, and rather than reactive, inefficient investment. For the research objectives, it largely depends on what the state of the technology is that we're studying. For proof of concept, prototypical, or other early stage technology, research objectives often ideally try to inform from a broad diversity of technical, design, and application considerations for the end user. NREL's Technology Development and Innovation Program and other DOE labs are sources and examples of such expertise. And with respect to labs such as NREL and Sandia, there are opportunities for test turbines to be provided as a laboratory as well. Conversely, near commercial ready technologies are looking for real-world experience and evidencing of their effectiveness, their compatibility, the reliability and durability of the equipment, and all feed in and largely help solidify market acceptance. These objectives strive to provide statistically significant results when responding to market questions about the effectiveness of a given technology. One of the key attributes of the scientific method, replication, also serves a practical function of evidencing performance and durability at multiple sites and in varied conditions, some of which can be considered some of the most hostile meteorological environments for sensitive technology systems to be operating in. The iterative steps of research and development and testing also provides insights for the technology innovator, vendor, or investor to focus their investment in the R&D process for a given technology. And as I mentioned before, the peer review publication of results is critical to transparently informing decision makers and market participants. Shifting now to some of the key elements and lessons learned, and starting with host site commitments. Real-world testing opportunities are a virtual necessity as technologies especially approach near commercial readiness. But operators need a value proposition for hosting such a study. So as such, looking for symbiotic opportunities is a key element to developing successful research projects. The operator's liability exposure increases when a third party simply steps foot on a facility. So the more the complex the scope, the schedule, and the budget of a research project, the more tangible and intangible the host site contributions are. Host sites lend insight to installation, integration, and operational constraints and opportunities, which provides a wealth of information and insight for technology developers. Host sites likely to be the frontline service providers for a technology's installation, integration, and operation. As such, the reliability, the durability, and the ease of their use will be a hallmark feature of those technologies that are successfully entering the market. And the breadth and the diversity of host site personnel and their expertise to support a research project is impossible to overstate. A point of illustration, if you recall my mention earlier of increasing liability exposure with third parties coming onto a wind facility, such a simple task takes a multiple group of parties within a company in sometimes unpredictable ways. So for instance, just having a third party come on the site introduces legal, insurance risks, on-site management, health and safety, just to name a few. Other areas of host site technical support I'll touch on here shortly. Before doing so, and closing this slide out, the data management and the movement of data is an increasingly complex challenge with variable interpretation and implementation of requirements across permitting processes can be at play depending on the research and the nature of the technology being deployed. And this at times goes for the landowner relations and agreements to lend their property to the participation of a research project. Lessons learned that we've seen in experiences to date is that probably principally operational needs tend to eclipse the research objectives. Paul touched on this a little bit in his presentation, whether it be the uncertainties from a pre-construction standpoint and even uncertainties for a fully operational facility. Research objectives and schedules tend to be oftentimes frustrated by unexpected or unplanned for changes in operation and other concerns that arise for the wind facility. And as I mentioned before, it takes a village. There is a variety of subject matter expertise that the host site brings to bear on a research project. Electrical engineers, IT specialists and security, permitting managers, and plant managers all play a critical role in making a research project successful. One of the key takeaways for parties coming into a host site is over-communicating is by far a preferred precautionary approach as opposed to under-communicating the needs of a research project, and defining the roles and responsibilities early on in a project, what the role of the host site might be, as well as any cost contribution, both direct and indirect, is critical to establish early on so expectations are established. Pivoting to the installation of the technology, a number of questions need to be asked. For example, the physical impact of installing a technology, how invasive is it? Are there physical fastening that needs to be done on a tower or in the cell or installed off tower? Or is it less invasive, such as using magnets or straps to temporarily install these technologies? This difference can be the difference between escalated cost or an excessive amount of time for design review. Installation responsibilities are oftentimes overlooked and need to be considered early on. Who's going to be doing the installation? Are those parties qualified for the types of hazardous environments and height requirements that are necessary for installing equipment? And also, whether the equipment is temporary or permanently installed will largely depend on what the nature of the research project is, what the commitments are by the host site post-research, as well as what impacts there might be to what would otherwise be standard operation of a wind project. The duration of the deployment for a research project will oftentimes create circumstances to be worked out in terms of routine operation and maintenance of a technology. If it's installed for a few months, there may not be nearly O&M requirements as there would be if it were, say, a 2-year study. And then other simple requirements, or seemingly simple requirements, such as power supply, need to be ferreted out fairly early on. This is particularly the case for off-tower technologies, which there really is going to end up being some seemingly minor but potentially permitted complex issues with grading, for example, a temporary power supply to an off-tower technology. And then even with on-tower technology, the power supplies from these turbines can at times be variable or somewhat dirty and need to be cleaned up. Low power, low voltage type technologies can be impacted from the high voltage environment that typically is found within a wind turbine. Lessons learned on these technology installations: the more involved the installation, the longer the lead time to coordinate with an operator and a turbine manufacturer, approving design considerations, finding the right parties within the host site or third-party installers to do the work. Clear installation instructions are especially important, particularly if you have a third-party installer under contract that's coming on to do the physical work. And never underestimate the variable nature of Mother Nature. Poor visibility, rain, sleet, snow, so on, can cause a considerable amount of complication and delays with not only installing technology, but throughout the research project. I mentioned before the unreliable and variable voltage power supply can sometimes be a complicating factor, particularly for low voltage systems. And the system design and installation approach should consider not just the accessibility of installing the equipment, but also the ongoing need for accessing the technology, whether that be technology that's monitoring for a research project or a technology that's being evaluated for impact reduction purposes. And then what should be underpinning all of the design and component elements of these technologies is the notion of reducing the O&M burden for the host site, increasing its market appetite. Moving then to the integration of the technology once it's installed, This is inserting the technology into the brains of the turbine, communicating with the SCADA system, moving of data, remote accessibility of the technology, all play a considerable part of a system's ability to seamlessly integrate with fairly sophisticated turbine technology. Thinking about the downtime of a wind project for the installation, maintenance, and decommissioning purposes of a project, the downtime that may be necessary to enable parts of the study, for example, flying trained raptors or drones or doing searching in and around or near the turbine, could sometimes create downtime that is otherwise unplanned for by the facility. And then the technology's operational integration at times, particularly for things like smart or informed curtailment, are all going to cumulatively impact the overall production for a wind facility. I mentioned data management, transfer, and security. There's the remote accessibility needs, the data transfer rates versus file size, large video data that's collected by a system represent large megabytes of data, sometimes like putting a golf ball through a garden hose in terms of the network systems that are in place out at these wind farms that don't contemplate these kinds of file sizes, and the frequency of which these file sizes are transmitted can be a choke point that needs to get resolved early on before the research project takes place. Network security, again, NERC and SIP requirements are a significant issue that needs to be considered and arguably can be construed as a competitive advantage for vendors who take seriously the idea of security requirements and understanding those and integrating those into their technology. Similarly, how the technology interfaces with the SCADA system, and it should be noted that the variety of different approaches that operators take to these kinds of requirements mean that it's rarely going to be a one-size-fits-all. Similarly, on required maintenance, the notion of developing technologies that reduce the maintenance requirements for an on-site staff that is already likely well staffed up in terms of workflow requirements of just operating a wind farm. Introducing a research project can oftentimes create additional workload for them. So working towards a system that has a lot of reliability and durability to minimize downtime, reducing the frequency of maintenance or troubleshooting helps with performing these evaluation tests and obviously having components that are designed to remain functional and reliable with long shelf lives is another key attribute of successful technologies. Digging in a little bit further on integration and talking about some complicating factors that come up. These factors tend not to be very conducive to research efforts, which are looking for a clean laboratory experience. Data security, as mentioned before, production impacts, grid stability, dedicated stop type tags that clearly identify for things like smart curtailment when a turbine has been paused in operation due to the element that's of interest, bad activity, for example, as opposed to some other reason for a turbine being stopped, such as answering grid congestion. Control and SCADA data interfaces are an important consideration as well as any kind of turbine impacts that may occur as a result of pausing operations for technologies such as curtailment. Signal to stop delays are varied across turbine platforms. Some turbine manufacturers' platforms have the ability to stop a lot sooner than others. Older turbine technology may not be as robust in its SCADA design to allow for the kinds of integration needs that a technology is developed with a mindset more towards newer turbine technology. The U.S. wind fleet is varied in terms of the age of technology as well as the differences across manufacturers. Some figures here will show some other elements that need to be considered. Topography plays a factor. If you're using a technology or a research project that's interested in a certain wind speed threshold for starting or stopping a technology, topography can play a factor in accurate measurements of wind speeds and the presence or absence of reference meteorological towers will also play an effect because the anemometers on these wind turbines tend to not be designed or maintained to be as accurate as some of these research projects would like. So wrapping up on the technology integration and thinking about lessons learned, understanding the system level requirements to facilitate the integration of technologies solutions on site, understanding the limits and uncertainties of the turbine platform, the wind assessment and technology sensors, system level controls that can't be compromised, third-party equipment that needs to meet data and security requirements, estimating and minimizing downtime for the purposes of the evaluation or the operation of the technology, and consideration of the full cost of deploying a technology, not just the capital cost of it, but the O&M and the operation decommissioning of those technologies are all things that are critical to a successful project. The evaluation studies themselves need to be developed within the practical limits of a budget, the host site's capabilities and limits, as well as what the turbine platform is capable of providing. That value proposition I mentioned before can't be understated. Leveraging pre-planned wildlife studies, for example, is a great way to seamlessly integrate a research project into an operating wind farm. The study plan and the schedule developed with a mind towards what the operational adjustments might be and achieving that operator's buy-in early on and clearly laying out in the study plan what the expectations are for roles and responsibilities. Any need of reprogramming a SCADA or enhancements to the SCADA are oftentimes something that needs to be done over a longer period of time than one would normally think. The requirements of SCADA programming can be complicated and present a multi-week, if not multi-month period of time in preparation for a project. And with this coming onto a site comes a lot of responsibilities, and Paul spoke, for example, of health and safety issues, not something that researchers tend to be that familiar with, and these wind facilities as large electrical generation facilities tend to have fairly significant and oftentimes variable requirements across operators. And then whatever permitting lead time there might be, whether those are doing permanent assessment or impact assessments of the work to be done, fees related to the permits, and can be oftentimes even greater for off-tower technologies, as I mentioned before, cultural resource impacts, habitat impacts, and what have you. In short, just be prepared for the unexpected and don't underestimate the power of uncertainty. As far as evaluation study results in the peer-reviewed realm, a couple of examples here to draw your attention to. AWWI, through private funding, conducted pilot tests on 2 technologies a couple, 3 years ago. The DT bird detection and deterrence system published results as an AWWI technical report want to draw your attention to this. Smith et al. Did a nice job of detailing the technical issues that they experienced, the solutions that they derived with their technology research efforts. That particular appendix in that technical report is a good opportunity to kind of see the blood and guts of doing a research project. Pivoting to the Identiflight system, McClure et al. Provided a good example, excuse me, the role peer-reviewed publications have in advancing the knowledge, informing the research and development, and further evaluation needs, provided a reliable performance evaluation for the market on that particular technology. And as a result of these two studies, we were able to shape and firm further evaluation, touching on that earlier idea I mentioned of replication, multiple sites, multiple years and environments, both of which these technologies are now being evaluated over a multi-year process thanks to DOE Wind Energy Technology Office funding with sweat and capital equity contributions from the wind industry operators as well as the technology vendors. Access to these studies are available on the AWWI results website and are good examples to look at with respect to what it takes to do these studies as well as how they lead to the next phase of not only the evolution of the technology, but also the informing further research. I want to thank you for your time and attention. Thanks again to the WREN organizers, and NREL particularly, for inviting me to present today, and all the talented scientists and technology innovators that are working to enable these market opportunities of technology. And Katie Battle and I are available to talk shop and engage about technology questions, issues, interests, and questions whenever you'd like. And with what time remaining, I'm happy to engage now on any topics of interest or questions from the presentation. Thank you.
Thanks so much, Stu. And thanks to Paul as well. Both our presenters developed great set of slides and information for us to think about going forward. In the interest of time, I think we're going to close down the webinar, but if you have questions for either Stu or Paul, please submit them in the Q&A box with your email address, and we can get responses for you to those questions. Thanks again to both AWWI and Kearns & West for hosting this webinar, and it'll be uploaded onto the TESIS website within a few days. Thanks everybody for joining today, and I hope you have a good rest of your week.